Let's look at OpenStack's College Physics Chapter 6, Problem 26. What is the ideal speed to take a 100-meter radius curve banked at a 20-degree angle? Let's start out by organizing our knowns and unknowns. So what we're given in the problem is that we have a curve that has a 100-meter radius. So I'll just write R is 100 meters, and it's banked at a 20-degree angle. So theta is 20 degrees. And what we're looking for is the ideal speed. So I'm going to write here speed. I have no idea what ideal speed means, but once I draw the diagram, maybe I can figure some things out. So a banked curve looks somewhat like this. So there is a curve in the road, and it banks at an angle of 20 degrees. Now, if we have a car on that banked curve, so let's say that the car is this way, and it would follow a path along this curve, then the forces that act on the car are the weight, and we know that the weight goes straight down, and the car is in contact with the road, so it has a normal force this way. And that is pretty much all that we know. Now, why would the car stay on that curved path? We might think that there is some sort of friction that holds it in, but the question is asking us for a speed that they call an ideal speed. So what does ideal have to do with all of this? Well, if you drive down the road and take an exit off the highway, you'll notice a yellow sign that gives you a number for a speed, 20 miles an hour or something like that. How do they determine those particular signs? Well, they're taking this ideal speed into consideration. So ideal speed is the speed that you should have, the maximum speed you should have, so you don't have to count on friction. So that means that the coefficient of friction between the tires and the road is 0. Basically, you have wintry conditions where the roads are icy. So that's what we mean by this ideal speed, that there is no friction holding the car on that circular path. So since the circular path goes somewhat this way, we need to have another force that keeps the car along that circular path. And if I look at the forces that I have here, I have the weight, which acts straight down, and I have the normal force that is perpendicular to the road. So the weight is not the thing that holds the car on the circular path. It has to be a force that is along the radius of the circular path, and the only force along this direction is the x component of the normal force. So I will break up my normal force into an x and a y component. So this is going to be my f and y, and this is going to be my f and x. And since I know that the centripetal force will act in this direction, so that's my a centripetal, then I will say, okay, I'll take my positive x-axis to the left towards the inside of the circle and my positive y-axis up. So now, when I write my sum of the forces in the x direction, the only force that acts is the x component of the normal force. This is the force that ideally keeps the car on the circular path. So the sum of the forces in the x direction then is just the normal force, and that is by Newton's second law, mass times acceleration, and the type of acceleration we have is centripetal, so it points towards the center of the circle. In the y direction, so sum of the forces in the y direction, now we don't want the car to hop up and down along the road, so we'll say then that the normal force in the y direction will have to cancel out the weight, so the sum of these two forces is 0. So I'm going to say sum of the forces in the y direction is Fn, sorry about that, Fn y minus W, and sum of those forces is 0. All right, so now I have two equations. So let's rewrite them. Fnx is going to be, okay, let's figure out the angles. So I know that this is my 20-degree angle. I also know that this is a 90-degree angle. So that means that this angle and that angle there, I'm going to make it a different color, yellow, I guess. So this angle here and that angle there are alternate interior angles, so they are congruent. They have the same value. Both of those are 20 degrees. But that means then that this angle plus that angle is also 90 degrees because the normal force is perpendicular to the plane, which then means that since the x and y components of the normal force also make a 90-degree angle, this angle then is also 90 degrees. So I'm going, 20 degrees, not 90 degrees. So those three angles are the same. They are all 20 degrees. So that means that my Fnx, so that would be this component over here, is actually the opposite of the 20-degree angle in this rectangle. So Fnx goes with a sine, and we'll write that here. So Fn sine 20 degrees is equal to the mass times the centripetal acceleration, which is v squared divided by r. In the y direction, we have Fn cosine 20 degrees is equal to mg, because up here we had that Fny minus weight is 0, so Fny has to be equal to mg. So now one little trick that I like to do is divide two equations like this, because when I do that, my Fn up here divided by Fn over there just drops out, and I have sine over cosine, which is tangent. The m goes away as well, so all I'm left with is tangent 20 is v squared over rg, and then when I solve for v, it's square root rg tangent 20, so that is square root of 100 meters times 9.8 meters per second squared times tangent 20, and when we plug numbers into the calculator, we end up with 18.9 meters per second. So that is the ideal speed that one should have on this banked curve, so that the car will stay on the circular path and not shoot out tangential to the path off the curb.